Today we're going to look at the inclined plane assessment with friction. This is slightly different than the original inclined plane that we did because of the fact that there's friction between the block and the ramp. I want to start by drawing the force diagram on the block when it's moving up the ramp. So if it's moving up the ramp, you know there's a couple forces on it. Obviously the earth pulls it down. We call that the weight. We label that mg, which is the mass times the gravitational field strength. There's still a normal force, the force of the ramp pushing the block perpendicular to the ramp. And we know there's some friction, but we'll get to the friction in a second. Let's take the weight and break it up into its component parts. There's an into the ramp component and a down the ramp component. Okay. We know the normal force has to balance out the into the ramp component. Maybe it's a little long. There we go. Boom. And now what about the frictional force? Well, the thing about this one that's interesting is that because the block is moving up the ramp, the velocity is the up the ramp direction. And in this case, the frictional force is opposing the motion of the block. So because the block is sliding up the ramp, the friction needs to be in the down the ramp direction. Now I'm going to put this here and draw it slightly less in terms of the size. And we might change the size based upon the value that we solve for if we were given numbers. So it might be less, it might be the same, it might be more than this down the ramp component, but at this point we don't know. And this one, of course, again, is the normal force. So we have three forces this time. We have the earth pulling it down, its components into and down the ramp, the friction, which is down the ramp, and the normal force, which is perpendicular. One of the questions we want to answer is, if we watch the acceleration of the block on the ramp, if the block were to slide up the ramp and then back down, is the acceleration of the block when it's on the up the ramp different when it's on the way down, and which of those is more? And it turns out it's much different. In this situation right here, what we can see is that the frictional force is in the same direction as the down the ramp component of the weight. So what that looks like if I draw it out is we know that the acceleration is equal to the unbalanced force over the mass. In this case, the acceleration is equal to this component right here, given this angle, right, the same as that angle. We're going to call this theta, actually. So this component here is equal to mg sine theta. So that component is mg sine theta. So the net unbalanced force would actually be equal to mg sine theta plus the friction, because they're in the same direction, over the mass. So we see that there's the sum of these two forces here. If we were to consider the block moving down the ramp, if the block were moving down the ramp, then we would have the frictional force, again, opposite here. And this down the ramp, the acceleration would be equal to mg sine theta minus f, because this time they're in opposite directions, over the mass. And so therefore, the acceleration when it's on the way up the ramp is the addition, and here it's a subtraction. So clearly the acceleration when it's on up the ramp is more than in the acceleration when it's on the way down the ramp. How do we solve for either of these actual accelerations given what we have here? Well, let's do this original one with it going up the ramp. Can I get an expression that relates all these quantities? Well, one thing I find interesting about this problem is that I can think about the frictional force in the context of the normal force and the coefficient of friction. So if I tell you that the coefficient of friction is the Greek letter mu between the block and the ramp, we can work with that. So our definition for this is the coefficient of friction is equal to the frictional force over the normal force, which is an interesting thing. So how do I figure out what the normal force is? Well, what we know is that in the y direction, the acceleration in the y direction is equal to 0. Therefore, the net force in the y direction is also equal to 0. Therefore, the normal force is equal to mg cosine theta, where this component right here is the mg cosine theta. So given that, I'm wondering if I can make a substitution. So the frictional force would be equal to mu times the normal. So the frictional force is equal to mu times mg cosine theta. If I substitute this statement right here into this original statement for the acceleration, I might be able to get something interesting where acceleration is equal to mg sine theta plus, make this substitution, mu mg cosine theta all over m. Now, because there's an m in this term and an m in this term, the m's can magically disappear. I'm left with a statement for the acceleration. It's equal to g sine theta plus mu g cosine theta. And obviously, if I knew the mu, I could solve for the acceleration directly. What if this is for the sliding, so this would be the coefficient of kinetic friction, and this would be the kinetic frictional force. If we go back and we look at this problem in terms of the context of what it would look like for the static friction, we can get an interesting idea. So I'm going to go back and get rid of all this. And the question is,